So in this week's lecture, what we want to look at is renewable energy. So we're going to start off at looking what exactly renewable energy is and compare it to non-renewable energy, and then we'll go through some of the different types of renewable energy. Please note that this week, this section is not in the textbook, so you won't find anything in the textbook. And again, like last week, this week's TAT and exam and test assignment questions that I can ask you on this section, I will not ask you any mathematical questions, so you won't have to calculate anything numerical. I will, however, ask you, as with last week, the sort of things in the TAT or things that are in this slide. So in terms of lecture objectives, what we want to do is, as I've already said, distinguish between the renewable and non-renewable energy sources. We want to determine what these sources of renewable energy are and look a little more in depth at each one of these. And then also we might look at some of the pros and cons. So some of the things might be renewable, but are they actually practical? Can we actually implement them, particularly in South Africa? Can we actually get them going? Do they work? And there are some renewable energy that actually might be more harmful to the environment than petroleum-based or non-renewable forms of energy. So we just want to take note of that, particularly in certain areas or uses. Okay, so just take note of that as well. Okay, so if we start with non-renewable energy. A non-renewable energy is some form of energy, so some fuel or other source of energy, that we cannot be remade or regrown. So once you've used it, that's it, it's gone. So the main examples of those are going to be anything that's petroleum-based. So that is typically coal, oil, and gas. So these types of energy, or these fuels rather, are formed many million years ago. They formed through various geological processes, and we now end up with these three. The other one that is non-renewable is also nuclear. Once you have used the nuclear energy, it is gone forever. You can't just replenish it. You can't turn the clock back and make more nuclear energy or any of these other types of energy here. So we've already said nuclear energy is created by the fission of uranium. So that's the division or the splitting of a compound into two or more parts to create the energy. So once it's been split, we are no longer able to create any more of this type of energy. Uranium in itself is non-renewable, so we can't make more of it. It can't be reproduced once that reaction, that fission reaction, has occurred. In the same way, as I've already said, the fossil fuels, the coal, petroleum, and natural gas, are considered to be non-renewable. So how is it that coal is formed? So like I said, many geological ages ago, we started with plants. So there were a whole bunch of plants, and this was here, as we've got in this diagram, before the dinosaurs even existed. So we had these plants, roughly 300 million years ago. When we look at 100 million years ago, so this is long time frames that we're looking at, these dead plants are now lying at the bottom of these different layers. So dead plants, dirt, and things started to build up on top of this. So you can see now these dead plants have been squashed so much that they've now formed coal. So that's how the coal and these other non-renewable energy sources are formed. So that heat and pressure has turned these dead plants into coal. So the diagram at the bottom here, we started with peat. Due to time, pressure, and heat, we get lignite and then the different forms of coal. Once we pull this up, there's no more coal left. We can't go back 300 million years ago to get more dinosaurs and more plants, and then wait another 300 million years to today. So any coal that you use now, because of the time it takes to produce coal, we see coal and other forms of the petroleum-based chemicals or energies as non-renewable. In a similar way, we can look at the oil and gas. So sorry about this, the quality of this picture. It is rather terrible. I tried to zoom it in and it just made the quality go bad. Again, we have tiny sea plants, sea creatures rather, let's call it, plants and animals. Again, 300 to 400 million years ago, these died. They then formed the bottom layers of the oceans. Sand and silt formed on top of it. These then get squashed. The sand, silt, and rock now built up quite heavily, and these plant and animal remains have now become oil deposits, again because of the pressure and the temperatures in all of those periods. Again, 300, 400 million years ago to today, any oil and gas deposits that we take out of the ground, we can't replace because we can't go back in that long ago in time. Okay, so in terms of renewable energy sources, what do we mean by renewable? Renewable is anything that we can use or we can make, or however we make that, and tomorrow we can get more of it. Okay, so it's not we're not going to wait 300, 400 million years to get these forms of energy back. We can get them back almost instantaneously. The first one that you can see there is the obvious one that everyone can think of, is going to be wind power. So wind power, the wind is going to be here today, it's going to be here tomorrow, we'll have wind forever. So if we can harness those types of energy, and we'll go through them in the rest of these slides, those types of energy, those aren't going to run out, those shouldn't run out, we'll always have it. Okay. In terms of what we've got on the slide, though, renewable energies are sources, as we say, that can be easily replenished within a short time period. So anything that is short, and we'll see what we mean by short as we go through some of these slides. It's fast becoming popular because obviously we've got various issues of running out of non-renewable sources, and some of them, depending on what you read and where you read it, some might run out soon, some might run out in many, many years' time. But obviously renewable energy is not going to run out. But the other thing is that these are often cleaner forms of energy. So wind, you're not making any pollution when you have this turbine swinging around. If you're burning fossil fuels, you are going to have some form of pollution coming up. Often these renewable energies can have lower operating costs, and the risks involved can also be lower. So you don't have high temperatures, high pressures, a lot of carbon dioxide, methanes, or not methanes, but other chemicals that are coming out of your process while you converting your fossil fuels into energy, so there are lower risks. And it's also an additional way to meet the energy demand. So it's not just that we don't have enough fossil fuels, but this is a supplement to supplement the energy supply. So South Africa uses roughly 70% of its makeup, of the electricity makeup in the country, comes from coal, so burning coal. And we all know what happens with the coal when it gets wet. We start with load shedding. So if we can have different forms of energy, including renewable energy sources, to start making alternate energy forms, then hopefully it'll ease the pressure on the grid and we won't have these troubles in the future. Okay, so if we look at in terms of the energy demand, so energy is used for many things. I don't need to explain what energy is used for. But since 1990, we see, and I'm not 100% sure what this is for. I'm not worried exactly about what this is for, but just I'm looking at the trends. So let's just look at 1990. We needed about 400, and what's this in? This is quadrillion, so it's 1 times 10 to the 15 BTU. So it was 400 in 1990. 10 years later, it was just over 400. 2020, we're now looking at over 600 quadrillion BTU. So the energy demand has increased as we've gone through. The OECD countries, those are the ones are typically the first world countries, the well-developed. You'll notice that that number, this light green, or sorry, not light, this dark green color has not increased that much. The non-OECD countries are all the developing countries in the world. So most of, or I think all of Africa, it's possibly all of Africa. So South Africa is a non-OECD country. So the OECD is Organization of Economic Cooperation and Development. The whole of Africa, so it's the developing world, and then most of China, South America, Russia, Asia, rather should I say. You can see these numbers. India is probably a non-OECD country as well, are starting to increase. So this is where the demand is coming in, the growing populations and the industrializing worlds. I'm going to come here because I'm going to forget about it later. You'll see this reference coming up quite a few times. It's the EIA.gov, the International Energy Outlook. So apologies again for these diagrams being a little bit poor quality. If you want to go and see the better diagrams and updated information, so I couldn't get hold of all the updated information in time for this presentation. That site has a whole lot of data, but unfortunately a lot of it is in Excel format. So that's why I didn't get around to updating some of these graphs. Although this one probably wouldn't have updated much in the last 10 years anyway. Okay, so now if we look at what exactly are we going to classify as the renewable energy sources. So this is a list that we are going to worry about in this course, and I'm not sure there are any others. So this should be a comprehensive list. The first one is going to be hydro, so it's the using water, so it'll be dams or other ways of using water. So that'll be a kinetic energy, the movement of that water to get something going for electricity. Another form of kinetic energy will be in wind. So the wind turbines, as we had before, the wind turbine spinning around will again produce electricity. Solar will be from thermal radiation. We've got heat from the sun, which will do something to something else, and we can get heat and or electricity to get our energy from the sun. Geothermal is basically hot water or hot, let's just call it water for now, hot systems in the earth that are far down and heated up by the lava and all that inside, or the magma in the Earth's crust. And that when that water rises, we can use the heat of that water that comes up for some form of thermal or heating energy as well. Biomass is any plant. So we can burn plants, or we can gasify, we can pyrolyze them. There are various different things we can do with biomasses, which we'll get to as well. The difference between the biomass here and the coal that we said before, when we talk about this biomass in the shorter times than the dinosaurs in the old times, the dinosaurs in that diagram that we had was 300, 400 million years ago, before it will replace enough of the plants to squash it down in the heat and temperature to make coal. The biomass we're talking about here will be a few years. So we can chop this tree down today, plant another tree, and it will regrow in a few years' time. So that's still a short time frame. Not as short as some of the others, but it's still short and considered a renewable energy source. The last two on here is tidal energy, so it's again a form of water, so there'll be some movements in this. And then the last one is ocean energy thermal conversion. So please remember ocean energy thermal conversion, because on some of the slides it just says OETC. Okay. If we start with hydropower, so it's a water or hydro, it's the same thing. Hydro is water. So hydropower is probably the one that you know the most about. It's the one that we all learn about in school, where we have a dam. So this is here the dam on the left. It's going to have the wall here, and we can limit the amount of water that flows through as we want, which then flows down through turbines. The turbines turn, it forms electricity in the generators, and this then forms the electricity. We have electricity flowing down the power lines as we need to. There are some systems of this. We have hydropower as an emergency backup supply. So what will happen is that during peak demand times, during the mornings and the evenings, Eskom, or the power supplier rather, will open up the dam wall. We will let the electricity go down to supply extra power to the community. Then during the quieter times, this water is then pumped back up to the dam, ready for use at a later time. The electricity, so this is it's used in Cape Town, where Cape Town's got nuclear power. So nuclear power, we can't switch it on and off, it's on all the time. So that surplus energy from Koeberg and the nuclear power plants will pump this water back up to the dam for peak times. It might not work so well in Joburg, because Joburg we use more coal-powered electricity, and coal-powered electricity you can actually switch off. You just stop putting coal into the furnaces. It's not going to create electricity. But this is an option for a peak power, as well as just a general extra form of electricity through hydro energy. So if we look at this in terms of the scale, so this is the sort of dam that we're talking about. This we can see is quite a big one. This is from overseas somewhere. I think it's actually in Canada. So there's a bridge. A car would probably be slightly bigger than the dot that I've got on this here in terms of scale. Okay, so it's quite a big wall. The water is then opened up through here, and there will be some generator or something formed in here. Again, this one is going to, as you can read on the slide, it's for the generation of electricity. So this is going to be for electricity. And obviously this one is going to be dependent on the water available. So in times of drought, if you've set up a big hydro dam system and there is no water, you're not going to be able to generate any electricity. In South Africa, we do have some hydropower generation. So we've got 1, 2, 3, 4, 5, 6, 7 dams all through the Free State, KwaZulu-Natal, Eastern Cape, Western Cape, and Northern Cape. Some were opened as early as 1977. This one here in 2012. I think I just need to check up on whether it is under construction still. I doubt it. It's probably either operational or been a very long process to get it going, I would imagine. That one there in KZN, 1,300 megawatts, so that's a gigawatt of energy. Some of the smaller ones here are only offering 2.1. So there's a various range of how much they can provide depending on the water available and what's been installed. You'll see these areas here, the Western Cape, Northern Cape, most of them are going to be where there is water. So if you don't have water, you're not going to have hydropower, which is kind of obvious. So I think I've mentioned some of these things already. The limitations of hydro energy, I've said, are location. Often there can be, and I'm not quite sure where this is in South Africa, there's competition with recreational users. So if you have a nice pristine river like this and you now decide to block it off, canoeists, other things might have a problem with you flowing down. In South Africa, where we have hydropower, we generally block it off to form the dam. So the main reason for the dam is the water to supply drinking water, not necessarily the energy. So we'll just have to double check that competition with recreational users. Environmental concerns, so the main concern is if you've built a dam, how much water is going downstream now? Have you stopped the fish and the plants downstream from getting the water that they need? So that's why often you will always have one of the sluice gates open on that dam, on these sort of hydropower dams, to let some of the water down so that there isn't as much environmental concern. The silt issue that is mentioned here is more a matter of that pumping scheme that I spoke of before. If you have one dam that has at the top and a dam at the bottom, and you're continually pumping the water from the top to the bottom. So pumping it from the top to the bottom, you're going to be loosening up the silt and pumping it backwards and forwards, so that could be a concern there. The advantages are that it's cheap to operate. You just need to have rain, water flowing through, and you can operate it. It can have a high energy yield, but you have to make sure that you have some water. Reservoirs, where this is used, and this is, the word is reservoir here, but this is also dams. They can act as flood control, so if you've got the low dam, obviously then you have a buffer situation that comes through that. The big one here, and why it's always promoted, well, why renewable energy is promoted rather, is that there's always going to be less pollution than fossil fuel combustion. Burning of coal and petroleum has smoke, whereas you're not going to have any smoke and gas coming off a hydro energy system. So some of the other problems with hydro energy, the first one being that it's a ground for disease. So wherever you have stagnant water sitting, so in dams and things like that, it's easy for bacteria and things to grow in stagnant water. I've already mentioned this. We are going to reduce downstream water availability. It can also affect the aquatic life, so any of the plants and things like that. Any of the fish that are trying to go upstream or downstream are now blocked by a dam wall where you've got your hydroelectricity. It can also have issues with dissolved oxygen concentrations as well as increased toxicity. And it can produce, so we already said there's no pollution from the gases that are being, from the coal that is being burnt, but because you have microorganisms in the water, if you start getting anaerobic or aerobic conditions and you get a high bacteria load, you can get some carbon dioxide and methane being released from the microorganisms if it's aerobic or anaerobic conditions respectively. The next one that we would look at is the wind energy. So I've already shown you the wind turbines in one of the diagrams before, and this will be the next one that we chat about here. Wind turbines can be very big. So those blades in those pictures that we saw earlier, and I can't go back to them unfortunately now when I'm recording these slides, can be hundreds of meters in diameter. So from the tip of the one blade to the center, I've heard, is of numbers of 100 meters. So these are very big things. These aren't little things that will stand outside in your or my home. They'll be out in the middle of nowhere, far away from everyone else. Wind is free, it provides clean energy, and there's no air pollution. So again, in the same way that we have hydropower, where water is turning a turbine, in this instance we just have air that is turning the turbine. And they're also going to produce electricity directly. So the turning the turbines is going to generate electricity. The advantage of this is that, well, not the advantage, but one of the things that makes this favorable these days, as you can see on this graph, is that in the 1980s, the cost of this was nearly 50 cents per kilowatt hour. And this is coming from a US site, so that'll be American cents, so it's dollar cents. And it comes and it drops down. So now in 2000, and again, we could probably go and check up these numbers again, it looks like it's about 5 cents. So it's 10 times cheaper in 20 years. So I'm not quite sure what it is in the next 20 years. I doubt it's got that much cheaper, but there you can see how much cheaper it's got. In the 1980s, it was almost non-existent. In the 2000s, the amount of energy or the installed capacity on this has increased dramatically. The US still remains the world leader in wind energy, but Europe has embarked on various wind power development programs. So in terms of what this is, and I've gone blank, this is the US data again. So in the US by 2030, the wind energy will supply twice the electricity it does now. So this data is 2013 data from what I recall. Okay, so from 2013 to 2030, the wind data is going to potentially double in the USA. In South Africa, we have also seen a tremendous growth in wind energy. So it's not just an international thing, but also in South Africa. So as I said, in South Africa, we are also looking at using wind energy as a form of supplementing our national grid. So as early as, I'm just trying to double check here, as early as 2002 at the Clipperville farm in the Western Cape, there was an installed capacity of 3. I'm just double checking. Yeah, installed capacity of 3.16 megawatts. Over the years, so we've got a 2008 here, and then 2013 and 14, that 3.16, a second farm in Darling at the Western Cape was added of about the same capacity. Then we now have other Western Cape who've now increased significantly, so that's 100 megawatts that are installed capacity that's planned, as well as the 67 and the 27 in the Eastern Cape, as well as the Western Cape in the 2014s. These numbers need to be updated on this, so it's your TUT question. I've asked you to look at what's been installed. So this has definitely been updated. I know there are more installations in the Eastern Cape. This number is probably quite a lot bigger now. You'll see that the operators on these, some of them are Eskom, so we are still relying on some Eskom power for this. But the other thing is that there are independent power suppliers now that are also adding to our national energy grid. So Metro Wind and Umoya Energy are now also adding to the production. The limitation of these, though, sorry, so let's just go back. So these might look small here. Some of these blades here, so there are 3 blades on this turbine. These blades can get up to over 100 meters long. So from that middle section to the top can be more than 100 meters. The limitation of this is it takes about 1,000,000 1,000 watt windmills to generate the same energy output as an average size fossil fuel plant. So you're not just going to place one of these poles up and replace an entire coal-based, coal-fired power plant. You're going to have 1,000,000 of these to replace one fossil fuel power or coal-fired power plant. That's the numbers that the average numbers. So some might be slightly different. Okay, so that's why when you see some of these pictures overseas, it's never a few next to each other. It is a lot. So this is a very small section here. There'll be a lot more. The second thing is that they can be noisy. So these things that turn around, they're getting quieter these days though, but as they turn around, obviously there's the noise of 1 fan times 2 times 3 times 100 fans. The noise does add up. There have been concerns as well that any birds that fly through could either get struck by these blades or sort of interfere with their migratory patterns. So that's the other flying animals would be bats. I don't know what they do with insects and things like that if they interfere with those. If the wind stops, the power stops. So we're going to have the same problem as in various of the renewable energy sources, that if the water stops in the rivers, you're not going to have hydropower. If the wind stops here, you're not going to have wind power. While these mechanisms at the top can turn and face the wind, so that they're not fixed in place, they will turn wherever the wind comes from. They'll be blown into the right direction. If there is no wind, there is no energy. The way that we overcome this is that we are going to have wind power if we have water power and other forms of renewable energy. It's unlikely that all of them will stop at the same time. So when the wind is not working, the water will supply us. When both are not working, one of the other renewables will help supply us. Okay, so that's what we mean the intermittent supply. So it must be coupled with other source of electricity. So either the renewables or the coal-based energy. As you can already see, we've already told you the scale and the size of these things. Because we need a lot of them, it's going to take up a lot of land. So it might be a good idea to have this where we're not using the land for something else. And obviously it's not practical in some areas. So it might not be practical because there is no wind, or it might not be practical because the land is being used for something else. We can't exactly start putting these huge things up in the middle of Johannesburg or in the Kruger Park where there's game reserves and things like that. So it's often difficult to find where the best spot is to put these. Overseas, and I don't think we're doing it in South Africa yet, particularly in north of Scotland, these get put into the sea. So it's out the way and out to sea, and then the electricity is brought back to land. Obviously, putting it in the sea has its own issues, because now how do you put this into the ground bed? The sea can't be too deep to get this down. And is that going to affect, previously it was affecting birds, is that now going to affect the fish or anything in the sea if we're going to plant them into the sea? Obviously, advantages of having wind energy, so it's not all negative. The first and foremost is that it's renewable, so we can always get it. It's not, wind will be here today, it will be there tomorrow. And once installed, the electricity is free. So obviously the construction phase is going to be free. It takes a lot to clear the area around it, put this structure up and the turbine and build all of this, but once it's up, it's free. It's a very clean source of energy. It's not impacting anything else. It's not harming the flow of the water. There's so much wind around, it's not altering the flow of the wind either. It can have a long operating life as well as a low cost of maintenance. So once this is up, you don't need anybody to come and fix it. It should go on for a very long time. I have said there is a cost associated, but it is actually quick. Relatively, it is quick and easy to build these things. Depending on where you're putting these, the land can be, so I said we don't want this in Joburg, we don't want this in the Kruger National Park, but you can see in this diagram here, or picture rather, there's a lot of open space around the bottom. So we could still be using this land for other things. There is some agricultural land we could be using here. This picture here, the land doesn't look the most exciting. So this is probably not farming land anyway. So you probably won't be using that land anyway. So it is a good competitor with hydroelectric power as well as fossil fuels in terms of what it can deliver. So yes, I did say that you need a lot of these units to compete with a single fossil fuel plant, but because it is so easy and cheap, relatively cheap to get up, it is a good competitor. In South Africa, we're probably getting, and I'll get you to check in the TUT now, we're probably getting to a stage where there's more hydropower than, more wind power than hydropower. But I wouldn't quote me on that. We'd need to double check that one. The next type of energy that we're going to look at is solar energy. So solar energy is, as the name implies, is going to be energy from the sun. And we can get a lot of our energy needs from the sun. You'll see a lot of development in Johannesburg these days, and probably other cities as well, where there are panels that are starting to be put up all on roofs of buildings, on car parks. I know there's a macro near where I stay that they replaced the car park and they've put shaded parking in where they've got photovoltaics on the roof. So the photovoltaics are going to use solar batteries and semiconductors to produce electricity. So that's the one form of solar energy that we can have. There are various others as well. So one is a solar power plant where we can use the heat of the sun to produce steam, which then turns turbines and produce energy. So we can take, so just to get back to that, there are basically two types of solar energy we can get. One produces an electricity. The photovoltaic cells at the bottom, so that's often called PV cells. We use that radiation to create electricity rather, or we can use the sun as a form of heat. So some people just use the sun to heat up water, but we can take that heat concept a lot further to produce steam and turn turbines to produce energy in that way. So here we've got one example of solar energy, as I was talking about, where people start putting photovoltaic or solar panels on their roof. So these photovoltaics they produce electricity directly. You plug your house into these photovoltaics, and then you can get energy through these arrows to play your TV, your light bulbs, your washing machines, and various other things. You probably do need an inverter just to convert the electricity to the right type of energy, at the correct rating. As with any of the others that we've discussed so far, when the sun disappears, the energy disappears. So this sort of system will still have an electricity grid that is going to be plugged into the system. So you will still rely on your energy from Eskom, so you can run this when the sun is no longer shining. There are some setups where this photovoltaic on the roof is really big, and the energy that comes from this will be stored in a battery. So it's not just this inverter, it'll be a whole wall. So this is the stuff that Tesla talks about, having the home packs of the walls, and then you can come completely off the grid if this is big enough and you've got the correct panels. This form of solar energy has come a long way in the last few years. So as you can see, as we had with the previous graph on the cost for wind energy, the cost for this is probably not as good as that, but the efficiencies of these panels has increased substantially over the last few years. The previous slide was for a home system. There are systems where we can look at the application to power plants, where we have a structure that is and there's one of these, and I'm going to get it's somewhere near Kimberley, out in the Northern Cape. So you have this very tall tower, and then the sun shines down and reflects off all of these mirrors. So all of these mirrors all of these slanted pieces here are mirrors, which I see they're called helostats in this one, which then direct the sun, and we can change the angle of this depending on where the sun is, to then reflect this up into a single point at the top. So the single point at the top then gets really, really hot, and it's typically there's some salt or other substance that's then melted up here, and then with that melting we create a flow. With that flow we can then get, it's not there, it's the top. There's an aiming point with another mirror which comes down to heat this purple section here. And then all of this gets heated up and we have some solar energy formed in these big towers. So those two are for producing electricity, but I also said we can also get these sort of systems to heat up water. So the heated water system is much easier. We have, let's look at the diagram on the left here, the sun's rays coming down onto these panels. Water flows through pipes. I'm trying to see where there's some sort of heater system here. So cold water goes through the pipe in the blue, it goes up, enters the top of the system, it'll then trickle down, so there'll be a high surface area to volume ratio on this thing here. The sun just simply heats up the water flows back down into the red pipe, and you can use that hot water to heat up you can use that hot water throughout the house. So it's for the bath, the shower, the kitchen, whatever else you might need to do it. The diagram on the right, there's also a similar thing we could do for solar air heating. So again, we're using the sun. We can then have heating solar panels, which they say here are optional, or we have openings, so it's not as high tech, but if we're wanting to heat our houses, we can have open panels, glass covered heat absorbing surface, so that the heat of the sun can then heat the house. I think for most of us, heating of a house is a foreign concept. This is more of an international, a European and North American thing, where they see snow for 6 months of the year. If you see snow for 6 months of the year, you do want to heat your house up. So they need to make a plan with that. So again, as with all of these systems, we are going to have limitations. So homes that only rely on solar energy can be very expensive to build. So with the whole Eskom and load shedding issue here, I'm sure a lot of you have been interested to see how can you get your own homes or your own rooms if you've got that, or just out of curiosity, what sort of costs do you go? So there are some systems that go into tens or hundreds of thousands of rands just to get some battery packs or to get the system going. So the other problem is if you over-insulate the house, you can aggravate indoor pollution. So if you're trying to seal your house to keep the heat in, if every single window, door, and all the other holes in your house are sealed, you're going to have very poor ventilation, and you can have a problem with indoor pollution. If we're looking at electricity, this can be accomplished, as I already said, by PV cells. These are so efficient these days that that's what you use for NASA. Okay, NASA is still only getting about 20% efficiency and can provide 50 watts of electricity per square meter. So when you compare the watts that we have in this calculation versus gigawatts and megawatts that we had in previous types of examples for the solar and the hydropower, how much space do you need to create an equivalent energy? Okay, so it will take up quite a bit of space. It does obviously have benefits if you've got empty roof space, a macro store that's got a roof space anyway, we might as well use that space. Okay, that 20% number, there are people working to get that number higher. Even a 2% increase on 20% is effectively a 10% increase. So minor changes still make quite a big difference to the overall watt number that you can get out. In terms of storage, I think I've said this before, so it can be stored in batteries, but large amounts of electricity cannot be stored. So while you can store some, it's still, most people are going from a day-to-day scenario for storing electricity. Anything that you've saved up is probably going to be used up overnight, and you need the sun to come out again tomorrow morning, obviously depending on how much you use. So what we need, again, is better storage capabilities and more efficient solar cells or the solar panels on your roof. The advantages, as we've had, we seem to be repeating ourselves a little bit on the advantages, and I think it's with all of the renewable energies, they are free. Okay, so once you've produced the system, you've got the system in, it's on your roof, it is going to be free with very little maintenance and operational costs, and only if something goes completely wrong, you will be having free electricity until this thing breaks. Again, it is a clean source of energy, and the low operating costs because you've got nothing. The same thing with the water, the solar, and now, sorry, the water, the wind, and now the solar. It is an intermittent energy source. So energy storage being still an issue. If the sun disappears, your energy disappears, so you might need to go back and rely on one of the other energy sources. And we've already said it, it has a low energy density. There's not much energy per area of that cell. The next form of energy is geothermal energy. So geothermal energy is going to relate to volcanoes. Effectively, that's the way that I keep on remembering it for some reason. And the heat that we get from magma, so that's this on the right here, the magma, which is inside the core of the earth, heating up water, which we then bring to the surface. So what happens is that this needs to be relatively near the surface of the earth. So it's typically in areas where there's volcanic activity or other areas where this magma has come up closer to the surface. This then warms the water, and we can drill a core down and take this hot water from this warmed up area from the magma. We take it up, do what we need to with the hot water, and return it back down afterwards as we need to. In South Africa, I'm not sure we have any of these. I've not come across any geothermal type applications. I've only heard these happening near volcanoes, up in Iceland, those sort of areas up there where there are thermal geysers. So the Americans, the geysers that they talk about at Yellowstone Park, there's some hot water that pumps up from that. If there are enough of those, you could use those. So the ones in America are the geysers at Yellowstone Park, as they call it. Those are in a national park, so they don't use those for this sort of energy. The diagram on the left, it says although hot surfaces near the surface are limited, so that's what I've already said. The Earth is hot everywhere if you go down far enough. I don't think we go down. I don't think we've tried to go far enough down in South Africa for this to work. So the applications of this depends on the temperature of the water. So depending how far up the magma has risen and what water is above it, how hot does the water get that we are now trying to take up. It can be hot enough so that it's used to power steam turbines. So that is common in Japan, Mexico, and the Philippines. And it's often built around the plate's tectonic boundaries. So wherever the Earth's tectonic plates meet and rupture and sort of form those, often where they do form those volcanoes, that's where this works quite well. It has applications beyond power and steam turbine, to power steam turbines, and it can just be used simply as a source of heat. So hot springs geothermal heat pumps. So using the hot water to heat homes and to heat other things and use the energy like that. So in terms of types of geothermal power, we have dry steam heat. So steam from the ground is used to turn a turbine. So that's the one we've already mentioned. It's used used into electricity, and the example there is in Iceland. The next one is a flash plant. So this would be water at temperatures of over 200. So again, in my mind, that would be dry, but that's the way they've defined it here. So just a reminder, dry steam is anything that is superheated, so there's no moisture into that. Flash plants using water at 200. The water is allowed to boil as it approaches the Earth's surface, so it's still fairly hot water. That water is then separated from the steam, and that steam is used to power the generator. So we had the first one in Iceland, the second one in Japan. Sorry, that's not a new bullet point. That should have been brought back onto the next line. The third one is hot water, so a binary plant where hot water flows through heat exchangers, which can then boil a secondary fluid. So if we have water, we remember water boils at 100 degrees Celsius. However, if we have water that isn't quite at 100 degrees Celsius, we can't boil water. So we need steam to turn the turbines in our generators. If the water is not at 100 degrees Celsius, we can still use it to heat up something else that has a lower boiling point. So something with a boiling point around 40, 50 degrees Celsius. If our water is 70 degrees Celsius, we can still vaporize that other fluid, and that other fluid can then spin the turbine. So we've mentioned that there are power plant options for this, but the other option for this, as I already alluded to, is that it is used particularly in Iceland, and here we also have it in Russia, where it is used to heat your home directly. So again, if you in South Africa, we don't know what heating your home actually means. Sorry, and I see there's spelling mistakes in this diagram that's been pulled off the net. we don't know anything about heating your home, but if you live in Russia and Iceland, where there are negative temperatures for many months of the year, you want to avoid freezing everything inside the pipes and everything else. So we can have warm water that comes up from geothermal means, which we can then warm our house in summer, that once that water is cooled down, we can send it back down again. Okay. This version here, I'm not quite sure how this one works. Doing the opposite, obviously in summer, you want to send the warm water down and the cold water comes up. So I'm not quite sure, this is new to me. There are obviously a lot of limitations with geothermal energy. I've already mentioned that in South Africa, how far down do we drill to get this? So it is very specific to location. So that's point 3 in this. It's not available everywhere. The other thing is that the geothermal fields can only be used for a period before heat extraction reduces considerably. So obviously, if you've now opened up a hole in the ground and you've got hot water that comes out and you're putting cold water back in, the energy or the heat in that water source is going to reduce. So at some point you have to close off that thermal field and let the magma from the Earth's core heat that water up again. So it's not necessarily, while it is still considered renewable, you can't use the same geothermal field forever and ever before you need to close it up and look somewhere else. So the thing is, it's easier to take hot water out of the ground, so this isn't really a limitation in my mind. This is probably more of a pro to this. It's easier to take hot water out of the ground than it is to heat it up again. So this is the thing with the limitations in terms of the point above. It can also produce water pollution. So in mining, so this is also, sorry, I need to stop. Sorry, I just had to pause. I had somebody at the door. So let's just get back to this point. We can produce water pollution from this. So anytime you are taking water from the ground, bringing it up, it's going to go through pipes, it's going to go through other things. I don't know what you're going to do with that, and then you're going to send it down again. You're going to get an accumulation, depending on what you're doing with it at the top of, or once it's on the Earth's surface. If you're adding chemicals or it's leaching materials out of metals, you're going to get you could get a buildup of salts, which then go back into the Earth, and then the pollution that way. This title says limitations, but right at the bottom we also have some advantages. So obviously, again, it is renewable. It's often actually very easy to exploit this sort of energy. There's less CO2 production compared to fossil fuels, and unlike some of the others, it actually has a high net energy yield. So the temperatures of the water that you can get out of these systems are fairly high. So the high energy, high temperature waters, you've got a lot of energy, so it's quite efficient in doing what you need it to do once it is out of the ground. Next, we're going to look at biomass energy. So as I said already, biomass energy is going to be from plants. So it's typically from plants. So those plants can be food crops, so crops like corn, things like that. It could be trees, so some form of pine or eucalyptus or any other thing that we could burn. It also can include algae. So this is going to be the energy that we get from burning any organic or living matter. So that's the biomass energy that we're going to be referring to in this section. It is going to be either living material, so it's obviously a tree that we've just cut down recently, or it could have been dead for a while. So obviously wood that we've chopped down and we wait for it to dry before we do this. Okay. Indirectly, this is a solar energy type of process because it's the sun and the photosynthetic process that happens, the sun shining down on the land, the trees grow, so it's the energy from the sun that lets the trees grow. So that's what this point here means in terms of a solar energy conversion. This point here is slightly contentious because it's saying it's a carbon neutral source and renewable energy. So the reason why it's noted as carbon neutral, because any carbon, so when we, let's start the other way around. If we take a tree and we burn it, so in the same way that we have fossil fuels, so coal and petroleum, when we burn fuel, we release carbon dioxide into the air. With trees, however, that carbon dioxide that ends up in the air is going to again be taken up by the next cycle of plants when they grow. So there's going to be continual cycling of CO2. So the CO2 gets absorbed by the plants when they are growing. When we burn the plants, it then gets released again into the atmosphere for the next cycle to come back in. So that's why we say it's a carbon neutral source. as well as renewable, because these plants, and this is not a plantation that we would cut down, this is a forest somewhere in Canada, if I recall, from when I got the photo. The plantations are renewable because we cut the tree, we'll start cutting down on one side, we'll move along, and by the time we get to the end of the plantation, the plants on the left, on the bottom of this diagram, have already regrown. So that's why we say this is renewable, even though it's a few years and not instantaneously renewable. So here we go, we've already got the idea of this CO2 cycling and why it can be renewable, and why it's carbon neutral rather. The other thing to note about biomass energy is that it can actually get us two different types of fuels. So the others we've already discussed, we can get electricity from them, we can get heat energy from geothermal and other things. For biomass, we can either go in two loops. So the first one, we take the plant, we get the truck, we put it into a power plant, so we burn this in exactly the same way as we do with coal. We then get electricity, the CO2 then goes back into the plants. In terms of the power plant, there's a lot of research going into this, into gasification and pyrolysis and various other things on how to get this more efficient. The other option with biomass, so these again could be trees or they could be other plant materials, is that we again take the truck and transport. There are now biological and chemical processes where we can convert the cellulose in these trees, in these plants, or the plant matter. We can convert the cellulose into basic alcohols, particularly ethanol. And from ethanol, we can put that directly into automobiles, so that's cars. And then obviously the cars then burn that off, the CO2 gets released and it gets back into the system. This alcohol plant, as per this diagram, should actually be rephrased as to a biorefinery. So there's a large area of research looking at how can you use biomass, so those complex sugars of carbohydrates, break them down into simple sugars. So one simple sugar can get converted to an ethanol, but you can also take those and create bigger building blocks. So we can start with ethanols and then build them up to methanols, higher order chemicals. So we're not just using them for automobiles, so we're using them in terms of other high-end chemicals. For this presentation, though, we were talking about energy. So energy is not going to be anything other than ethanol for this course. So ethanol will be put into plants, into cars to then burn and close this cycle. So traditionally, we have used wood as a fuel. So wood has been a fuel for us since we were cavemen. So we used wood as a form of heat, a form of cooking, and various other things. We can also look at biodegradable waste such as manure, crop residues, municipal solid waste, and sewage. So it's no longer just a matter of chopping down forests and plantations, but there are other types of things that we can look at. So crop residues will be after the farmer has been through his mealie field, his maize and corn, any of those wheat stalks, or the wheat stalks, the corn cobs, things like that. We could look at those sort of things for energy. Municipal solid waste and sludge, so we had our water discussion a week, 2 weeks ago, whenever it was, and we said that there was that solid sludge that came off the wastewater treatment plant. What do you do with that? So that digester, you can use that for energy. There is, however, a slight problem with some of these things. The first one is going to be the agriculture. So agriculture, if we could theoretically use any biomass from agriculture for energy, but we don't want to be using, or we might not want to be using, things that people could be eating. So particularly in Africa, we have got famine in certain areas. Should we be converting corn and things we eat into energy? So the answer is obviously no. If we had a surplus of that, though, then obviously that is an option. In terms of those agricultural products, in terms of those agricultural products for energy crops, though, there should be a high yield and low maintenance crop. So you don't want to be putting more energy into growing the crop than you actually get energy out. So some things that are good examples are sugarcane. It grows fairly easily. Palm oil in certain areas, it's a very quick and easy growing crop. The other issue on this is the use of genetically modified plants. So how much do you want to spend on genetically modified plants? And the ethics around that is a discussion for another time. So these crops, as already said, we could produce a liquid. So that's the ethanol that we've been talking about. Once you've got an ethanol, it's fairly easy to convert it into a gaseous biofuel. So if we break the biogas down, in the absence of CO2, we can get some bioethanol. It is basically from the fermentation process, and this one is usually corn, so it's maize and mealies, and we break this down into an ethanol that we can then use for powering plants. There's a second route which we could also make biodiesel. That is typically from an oil or other vegetable oils, where we convert the oils through transesterification, so you add sodium hydroxide and a catalyst, typically a methanol as a catalyst, and then you can make biodiesel. So the problem with that one, as you can probably see there, is that the rapeseed oil or the vegetable oils are typically things that we want, whereas the bioethanol route, we can use cellulosic waste materials, so grasses, switchgrass, so it's slightly different starting material and a different competition for for food or not. Okay. So again, I've referred you to the US Energy Information Administration. The website was on a previous slide. So the demand for the total energy production, rather, from biomass from 2011 was about 4, and I'm not quite sure what that unit is, sorry. I'm not worried about the units, I'm just worried about the increase. So we've gone from about 4, and this was in the States. There was a slight drop in 2012, but then from 2012 onwards, there's been a steady increase in the supply of this biomass. Okay. So again, you can see 2040, there's a predicted increase. I don't think this graph took into account COVID, so we might want to just look at the updated version of this. So there is an increased demand and a supply of biomass energy as well, as much as we had for the wind energy. Okay, so if we look at ethanol, so ethanol in million liters. So it was used mainly as, if anybody asks what is ethanol, most of you will tell me it's that thing that makes you drunk, beer and wine, and that is what we have in this red portion. So the red portion is the ethanol that we have from alcoholic beverages. So that's the red in a beverage. So you'll see from 1975 to 2010, this red bar has stayed relatively constant. It gets a little bigger up in 2005, 2010. There are also industrial uses for ethanol, so it could be used as a starting material for other chemicals. It's also used as a cleaning agent, so I'm sure we all know about COVID and the ethanol contents and things like that in our hand sanitizers. So this is this yellow bar here, and as you can see, it is fairly constant. So this is up to 2010. The fuel component now, so the ethanol fuel component has increased substantially. So this is the one that has actually grown. So from about 2002, 2003, there was a slight wobble here, but then from there onwards, it's now increased substantially. So it's now by far the leading contributor, or so the leading demand, I suppose you'd say, for ethanol by industry. Okay. Again, if we had to extend this, and I couldn't find one for 2019, 2020, 2021. The demand for, particularly in South Africa, the demand for beverage was taken away from us. The demand for sanitizers went up, so this yellow bar probably tripled or quadrupled. I'm not quite sure what the fuel one did. Okay. But the main point is that we can see that there's the need for energy, from fuel from ethanol. So ethanol is actually an alternative to gasoline. So gasoline, I've used that word gasoline there because that's the good old American. It's the alternative to petrol. So ethanol in petrol or in gasoline is given an E number. So E numbers describe what percentage of ethanol is present in a fuel. So if you see something that says it's E25, E10, E5, it means that there is that percentage of ethanol in a normal petrol system, petrol mix. Okay, so the example there, E85, there's 85% ethanol, 15% petrol. So anything that is low, so you've got E5 to E25, it's called gasohol, and I've not actually come across that outside of textbooks. Anything higher, I'm not sure if that has a specific name. Anything from 0 to 10% ethanol, so this is at the bottom here, is normally fine to run in any engine. So ethanol has a similar makeup to the petrol that you put in your car. So if you've only got 10% ethanol, it's not going to affect your car too much, and it should operate. It should. Please don't do it if you find it without checking with manufacturers. It should operate perfectly fine. Anything higher, there might be some alterations that are needed. So this is in petrol tanks. I don't think there's a slide on on biodiesel fuel. So biodiesel would obviously go in a diesel tank. You replace that with diesel, obviously not with petrol. So ethanol replaces petrol, biodiesel replaces normal diesel. So the one thing just to note is that Brazil is the world leader in ethanol production and the utilization in cars. So the reason that they are the world leader is because they pretty much have a monopoly on the sugarcane production in the world. They have the largest supply of sugarcane in the world by far. So they have surplus sugarcane that they can convert, either the sugarcane or the bagasse and the leftover wastes. They can then convert that into ethanol. So obviously, if they've got the supply of ethanol, they can use it in their cars. Okay, so the advantage of biomass energy, so it is versatile. We can use it as either a direct burn, we can burn it directly through pyrolysis and gasification to form electricity. We can use it as a ethanol, we could use it as a biodiesel, we can use it as other chemicals. So that's what we mean by versatile. It is still renewable, even though it takes a few years for some of these trees to grow. One way around this has been the investigation of things like algae, so using algae instead of trees, so algae grows very quickly. The problem is that algae takes up a lot of land space, so it's not actually any more advantageous than a tree. Ideally, it is a net zero production. So we've mentioned this before. Why we've got the word ideally there is because obviously if you are cutting down trees and you've got other processes involved, you need energy, and that energy is going to be emitting CO2. So if you could cut the tree down without emitting CO2, without chainsaws and producing things without emitting on the secondary processes, it would be net zero. It is still by far going to emit less CO2 and NOx gases than any of the fossil fuels. So any of the the NO234 NOx gases is going to be much lower than that. The disadvantages of this are that it has a low energy density, so you're going to need a lot of biomass to get what you need. There's always been a problem with land conversion. So where do we actually do this? Do we cut down the rainforest to put in these sort of plantations? Where do we actually do this? There's going to be biodiversity loss. There may be also a decrease in agricultural food productivity. So as I already said, we don't want to compete with food for the energy, but just by having the land space, are we actually running into that problem anyway? Okay. So there are also going to be as I know the word here as usual, there are going to be problems with intensive agricultural activities. So there could be soil depletion, soil erosion, and other aesthetics type issues of having a tree that's now coming into this area. We're also going to have issues of increased fire risk. So places like Cape Town that have had those big fires in the last few days, there are plantations on the mountain, and some of those trees that are the pine trees that are close to those areas, not necessarily part of the plantations, can lead to a risk of fire. The next one we're going to look at is tidal energy. So tidal energy is going to be different to the hydropower in the sense that the tidal energy is going to be 100% from the sea. The idea of this first one, or this first option, is that we have a large body of water and we get a large flow. So when we have the tides coming in, so the water is high on the outside, we have high tide on the left-hand side here, and that water rushes in through, and again, it's a straight kinetic energy conversion. There's the turbine again. The water rushes through, turns the turbine, and we have electricity. When the tide goes out, we then have this water rushing out. The turbine then turns. This might flip the other way. Whichever way it is, it's not necessarily going backwards. This water comes out again, and it again turns this turbine. In terms of this backwards and forwards, so we have 2 high tides, 2 low tides every day. So we'll have this backwards and forwards. There'll be a 4 times 1, 2, 3, 4 for the 2 high tides, low tides. Obviously, when we reach the peak high tide, there's going to be minimal movement. It's going to happen during the changing of the tides. Okay, this one is probably a little bit more reliable than both the wind and the solar, probably and the hydro as well, because the tides are always changing. With some of the other options that we've had, as we said before, if there are some clouds, we don't have solar. If there's a drought, we don't have wind. This one is potentially a little bit more reliable. So the one thing that is important with tidal energy is where you would locate this. So there are some areas in the world where tidal, or the difference in the tide heights, the difference between low tide and high tide, is more pronounced than in others. So in this diagram, we've got, this is Canada. So there, New Brunswick is part of Canada. So New Brunswick all the way around Nova Scotia. So this is on the border of the United States. So there's Maine on the side here. You can see that each of these points, there's a difference in the tidal heights. So we've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 meters. Okay, so there's a 14 meters here. So if you have a high tidal difference, the potential energy, there's obviously that height difference in the water. So when that kinetic energy comes through from the change in the 15 meters, sorry, more than that, 16 meters, you are going to have big changes like this. If you don't have as big changes, you're not going to be able to work this as well. The other concern or potential issue is that if we have something like we had in the previous diagram where we want to set up something like that, you probably want it somewhere where there aren't terribly wild seas. So you don't want something that is completely unmanageable. You need to be able to have somewhere where you can build that system. So by the look of this, we could probably build some sort of system here. We need the right land and sea combination to get this all going. Another form of tidal energy is just to put multiple of these poles down, and then we can run these through. There is no dam, so as we obviously said, but there is a turbine. So we can get the kinetic energy, so that's the currents that are ebbing and flowing. So it's not, the currents flowing, or the tides rather, so it's the kinetic energy of the currents between the ebbing and surging tides, so it's the same thing, which are causing this kinetic energy that's going through here. The other energy that we can extract, and I started mentioning it earlier, was that we have the potential energy. So if you have such a high height in the tidal difference, that potential energy that you've got, the up-down movement, can also help us get some form of energy or renewable energy from the sea. So there are also systems like this. So this is another example of exactly the same thing, I think it is, where we're almost building ourselves a dam. So you build a wall into the side, into the ground, and then this wall up here, so that when at the top we have a high tide, the tide rises on the outside, and it's forced, there's only one opening through here. So there we have a higher pressure on the right-hand side because the tide is high, and all the water will push through and power the turbine. When the tide goes out, the water is then lower on the right-hand side, so we again have this height difference, and we now effectively have a dam. So this is the same logic as we had for the dam earlier. We then push through that turbine, and then we can again generate electricity through that system there. So the other thing we can do with these turbines, so we don't necessarily have to have them right next to the coast, as I was mentioning. We could also be placed on the ocean floor where the general flowing water can just turn these turbines. One turn of a 100-foot propeller can produce 1 megawatt of electricity. So that picture there that I've got in front of us looks very similar to what we had for the wind power. So now we have a similar idea, but we now put this under the sea, so we're going to have these turbines here. The problem, however, is if you put any sort of metal or any other system under the sea, we are going to have corrosion. So these are going to obviously corrode. Once they corrode, you're going to have some sort of problem with the operation of those. And also, how do you install those? Installing those on land is fairly easy. You just go out there and you put it on the ground and you put it up. It's a little bit more complicated to put this into the sea, where you want to anchor this to the sea floor, and it's also going to require a little bit of maintenance. So the wind generation, the wind power, was turning these quite freely, no problems. Once these start corroding, how are you going to come in here for maintenance? The other problem is that the best tides are often at the poles, so North and South Pole, so that's far away from people. We want to be closer to where people are. Another form of energy is going to be the ocean energy thermal conversion. So this one I have not come across very often. So I'm not sure how often you will see this. And just for the next few slides, when it says OETC, this is the Ocean Energy Thermal Conversion. So the idea of this is based on temperature differences. So it is, again, a clean energy, and it's going to exploit the temperature difference between the warm surface water and cold water at a depth. And from this, we are going to run a heat engine. So the same thing that you would see in your thermodynamics courses this year in terms of heat engines, we will have the same thing here, but with water in the ocean from the hot water and the cold water. So hot water at the top and the cold water at the bottom. So just as a reminder, but I think you do need to go to your thermodynamics course, the heat engine is a device that is going to be placed between a high temperature reservoir and a cold temperature reservoir to produce energy. There are various different types of heat engines, and depending on where you are and what's happening, will decide how you're going to choose that for the OET system. So if you see your thermodynamics textbooks, you will see a similar diagram to this. So this is exactly the same as what we're looking at in the OETC. There is going to be a pump. There's going to be some form of heat exchange with a compression or a this is an expansion. Compression, you will then have a expansion over a turbine where the energy is then captured at this turbine. You can then have the gases flowing around, another heat transfer with a pump to pump this through, and we can have a closed cycle. In terms of water here, you'll see there's water coming in at 5 degrees Celsius and coming out at 10. On this side, there's water coming in at 15 degrees Celsius and out at 10. So this, in my mind, is the wrong way around. We were talking about the hot water being at the top, so this should actually be higher than this one because this is the cold water that's coming from far down in order to do this. The problem with this is that we need temperature difference to be at least 22 degrees Celsius. So for those heat pumps to work, you need to have a temperature difference so that you can actually get this flow going without using energy. So you actually gain energy out of this. So in order to do that, there's some zones in the world that are more reliable than others. Particularly this is around the equator. So there's a zone there that is in the red. So you'll see on this map here, there's in the red. So anything more than 24 degrees Celsius temperature difference is probably going to be ideal for this. So this map of the world, there are very few areas where this will actually happen. So the best for this is around the tropical islands. Before I click on the next slide, just let you accidentally get out of this presentation. Again, there is no chapter on this in the textbook. So you'll have to rely on these notes as well as any other readings that you come up with. Please remember, on Friday, we will have a voluntary consultation session again. So these have been attended by about 12 to 15 students with very few questions asked. Don't forget, you still have the discussion board. So if you want to use the discussion board for general queries, please also use that. We've got the tutors that are reading through those. I'm reading through those as well. So if you have a query today, please go and put your query on that discussion board and don't wait until Friday. Otherwise, thanks, and I will see you on Friday anyway. Cheers.